ties together with the enthalpy and the internal energy to give us the values that we want. Let's see, next page. Constant volume process. So here we have a constant volume P versus T, and the volume is constant, and we can do exactly the same thing. We can start out the given conditions, and the volume remains constant, so there's no work done along here. We've clamped this. And so the volume cannot change. But what happens then, as the temperature changes, the pressure is going to go up or go down. Think of a bomb calorimeter. When you burn something in a bomb calorimeter, the volume is constant. Gases, or whatever burning, you go from something solid to carbon dioxide and water, and they're in the vapor phase because you're burning, and the temperature goes up of that. Well, you get pressure increased in that constant volume because it can't expand, but there's no work done in this process. So all that happens is the internal energy and the enthalpy depend upon a change of heat in there, and there's no work done at all. So when you go along here again, along the curve, the ideal gas law is maintained all the way. And if I wanted to go through an irreversible path, you would do something like suddenly cool it or suddenly heat it, and you could suddenly heat it and you get back to the same place through a different path. But there the heat is involved, but they'll cancel by the time you get back to the same point. So the reversible path will give us the same as these irreversible paths for the state functions, even though the paths give you different heat. So in this particular case, we just say the volume is delta V is 0. It's maintained at 22.4, and therefore